All right, everyone, this is it. So we are going to start with the first topic. Now, of course, the first week and maybe the second week also, I'm going to review some stuff from statistics that you need to know to follow the course. Okay, so there's going to be some theoretical concepts that I'm introducing to you. Okay, you don't need to write them down, but these are the most important ones. Especially linear regression is a huge part. So this is also something which I'm going to review maybe next week. This week I'm giving you some basic statistics. Okay, so this is not about time series directly, but it will based on, I will use these tools, so just for you to know. Okay, so that's going to be the part of the first chapter, introduction of the book. Okay, so you can check it out. And the things I'm going to talk about today are going to be the so-called CDFs of random variables, cumulative distribution functions. So you see what it is, and I'm giving you examples how to establish them, this and that. Cumulative distribution functions, okay, expectation and variance. Of course, we're going to look at some moments of linear transformation. So if I say moments, usually I mean the first and the second moment. And then, of course, you can make it to the expectation and the variance itself. So we're going to look at expectation and variance of so-called linear transformations of random variables, of course. And then today I'm going to generalize that concept by looking at the so-called transformation theorem, which is basically a general transformation, more or less a general transformation of a random variable. Okay, so not just the linear, but that incorporates also the linear transformation, but not just that, any other transformation. Not any other, but to be precise, but let's say the most common ones that are going to be captured that. So maybe you never heard of that. Okay, so that's going to be something new, but it's not difficult to understand. So therefore, I was including in it as well. Again, I'm going to use these things quite frequently, especially moments of linear transformations, especially that. So this is going to be a major part, okay, because in time series, I need to calculate expectations, variances, autocovariance, and this and that. So you see how it's going to work. So please pay special attention to that one. Cumulative distribution functions, these are more theoretical. Okay, so you would not need to do this in empirical work because it's relatively difficult to, let's say, to estimate cumulative distribution functions in practice. And yeah, but this is just a theoretical consideration. I would like you to define independency. So based on that, I would need that as well. But there is actually no other consideration what I would, use cumulative distribution functions, maybe in hypothesis testing. So that's an exception. But any other application is not basically based on that. Now, a random variable, to be basically just, to simplify things, is just a function. So it's going to be a real number, in this case especially. So you have a real number coming out of that function. And what you need to put into that function are going to be outcomes of a random experiment. So every random variable is going to be based on a random experiment, guys, okay, which is an underlying random experiment. It's not explicitly told what the random experiment is. Okay, and then you have basically a real number depending on the outcomes of that random experiment, so which is basically underlying here. Again, but the random experiment is not specified directly, so it's only indirectly there. Okay, so we have a function that maps basically outcomes of a random experiment, which are captured by omega. So omega is going to be the so-called sample space, and the sample space, on the other hand, is going to be a set that has elements, of course, which are the outcomes of the underlying random experiment. It's not clearly specified in most cases, and that maps elements on the set of real numbers. So what you plug in are going to be outcomes of a random experiment, and what you get out is basically going to be real numbers. So real number, basically depending on outcomes of a random experiment, is going to be a random variable. Keep in mind, guys, that this definition is not precise, to be honest. Okay, so there is a more specific and more accurate definition based on that, but the scope of this course does not go beyond that, so you don't need to look at, Borel sets and stuff. There is measure theory, which is a little bit more complicated. I do this with my PhD students, so if you do a PhD course, then you will see what the random variable is, in particular, what the random experiment is in this setting, but not this time. So again, that's going to be enough. So it's simply enough, basically, just for you to remember that a random variable is simply a real number depending on a random experiment, okay, which is not specified most of the time in practice. Omega is going to be the sample space containing every single outcome of a random experiment. Okay, so that contains everything that you have regarding the random experiment, so they give you the full information about it. And then you have x, which is basically the random variable itself. So that's the function. Okay, so when you have a function, you always have an input and you always have an output. The input is going to be the outcome of a random experiment, and the output is going to be a real number, and the real number is depending on that. So basically, real number as a function of outcomes of a random experiment, and that's what the random variable is going to be. Now, the things that are going to come out after that. So again, when it comes to a function, you always have an input and you always have an output, and if you know what the output is depending on the input, then you can basically specify the function. So there's not going to be like equations and stuff here. Okay, so the function is specified if you know what comes out when you put something in. And the things that are going to come out, real numbers are going to come out based on that, are going to be called realizations. So these are the images. Okay, so images are basically the elements that come out basically from the function. Okay, so when you put in a outcome of a random experiment, you have real numbers coming out, and these real numbers are called realizations. Okay, so if I say realizations, possible realizations to be precise, then these are going to be the values that the random variable can generate, technically speaking. And you need to know what kind of values these are. You understand what I'm saying? This is it, guys. So I don't go beyond that, but keep in mind, this definition is not accurate, to be honest. But again, this is just the scope of this course, so I don't go beyond that. You don't need to do measure theory and Borel sets and this and that. So this is not going to be about that. Now, there is a concept related to discrete random variables, which is going to be the probability mass function. Okay, so probability mass, it doesn't have to do with it. It has nothing to do with the mass. You understand what I'm saying? So this relates to the discrete random variable. A random variable is discrete if its outcomes are countable. So you have something like 0, 1, 2, 3, 4, 5, 6, this and that. So that's going to be a discrete random variable, and you can basically characterize them by their probabilities. So I will say P of something is also a function of events of a random experiment, and the event is going to be, in this case, this time, if capital X denotes the random variable, that the random variable, let's say, is equal to 1. And that is basically representing the probability that it is going to happen. So what's the probability that X is going to be equal to 1? Again, it depends on the random variable itself, but let's say it's just going to be 0.5. Again, it's not always 0.5, of course, but let's say this is just an example. Okay, so let's say the random variable X takes values, or this basically takes the value 1, which is 0.5. Now, of course, 1 is a realization. So if the probability is positive, then it's automatically going to be a realization of a random variable, so the image of the random variable, right? This is it. And then, of course, you have more. In this case, so let's say X is equal to 2. Let's say the probability of that is going to be 30%, and the probability that X is going to be equal to 4, let's say, is going to be 20%, okay? Is this understandable, guys? So this is called the probability distribution of the random variable, and the random variable is discrete because a set of its realizations is countable. Okay, I will talk about that concept maybe in the following lectures. Okay, but everybody should have seen this. Now, again, realizations are basically the real numbers that can come out. Okay, so that basically can be generated. These are going to be 1, 2, and 4, of course, and there is no other, because the sum of the probabilities is going to be equal to 1, so the total sum is, of course, equal to 1, and there is basically no chance, let's say, that the random variable would have another realization, or maybe we would say that the random variable does not take anything else. Almost surely, that's the term, but I'm going to come back to that later on, okay? Do you understand what realizations are in this case, again, for this discrete random variable? All right, guys, so then, of course, there is a probability mass function, which you're going to see, so this is not what it is. I call this fx, okay, so basically, or f of x. This is going to give you the probability that the random variable is equal to a certain value. So let's say you take the probability mass function at point k. Okay, so you put in basically the value k into that. This is going to be the probability that the random variable is exactly equal to that value. And that's what it's going to be about. So in this case, you have them already here. This is going to be the probability mass function at point 1, of course. So if you put in 1, you have the probability coming out that the random variable is equal to 1. If you put in 2, then you have the probability coming out that the random variable is equal to 2. And if you put in 4, you have basically the probability that the random variable, is equal to 4 coming out, which is equal to 0.2 then. Okay? And then for the sake of completeness, if you put in anything else other than that, so let's say I use basically the notation k, all right? So then, of course, this is going to be 0 if k is anything other than basically 1, 2, or 4. Okay, that's for the sake of completeness. I added this to this consideration. All right, so every other realization has 0 probability then. So that's not going to be a realization by definition, because the random variable cannot generate those. Okay, so that's why I don't write it down explicitly, but that's still a correct statement in this consideration. Is this understandable, guys? Okay, so that's that. Now you should have seen this actually, or something like that. Okay, there is lots and lots of discrete distributions. For example, the geometric distribution, the binomial distribution, the Bernoulli distribution, the hypergeometric distribution, blah, 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 blah. So there are a lot of them. Okay, this distribution has no name, of course, but that is a discrete distribution, what you see. And this can be described by the probability mass function. So if you know the probability mass function of a discrete distribution, then you know everything about the distribution itself, provided, of course, that the random variable is discrete, which is the case here. And there is also the cumulative distribution function that is also true. I mean, that is also existent for both discrete and continuous ones. Especially for discrete ones, how do you get basically the cumulative distribution function, which I call capital F this time, let's say at point 2. Now, first off, you need to understand what this is. This is going to be not the probability, okay, so I call this CDF. So if I say CDF, this is going to be the cumulative distribution function hereafter, okay, so because the term cumulative distribution function is quite long. So I will say CDF, all right, so just for you to understand this. I will use the term CDF all the time, okay, so let's say the CDF of basically of the random variable x at point 2 would give you the probability that the random variable is not greater than 2, in contrast to the probability mass function, which will give you the probability that the random variable is equal to a specific value that you put into the probability mass function. But again, here you have the probability mass functions, and that is the CDF, so that's something else. Okay, so that's going to be on this slide. So again, probability that a random variable is not greater than 2, and this concept is, of course, it does exist for discrete random variables as well as continuous ones. So for example, the normal distribution, you might heard about that, is a continuous distribution, so you can specify cumulative distribution function. Technically speaking, for every random variable, there is. So every random variable actually has a cumulative distribution function, both discrete and continuous, or neither. There is also random variables that are neither, okay, but in practice, it's not going to be that important. Now, how do you get basically that? Now, since this is a union of events, basically of these two, okay, so because if x is not greater than 2, it means that it's either equal to 1 or to 2, so that event basically constitutes a union of these two, and the probability of a union is going to be, so just for the record, if you understand basically what I'm saying, the probability of a union is going to be the sum of the probabilities of the corresponding events, provided that the events are disjoint. Sorry guys. So if the events are disjoint, which means that their intersection is empty. So if the intersection is empty, then of course the probability of a union is going to be the sum of the corresponding probabilities from which the union is constructed from. Okay, so there need to be pairwise disjoint. That's a term. Maybe you remember that one. If basically, again, if a union consists of pairwise disjoint sets, the probability of a union is going to be the sum of the corresponding probabilities, just as the case here, because trust me on that, this event here, that the random variable is not greater than 2, consists of a union of these two events. Okay, so either it's equal to 1 or to 2. These are the only possible scenarios that exist. Do you understand what I'm saying? So this is going to be it. And therefore, you need to sum up the corresponding probabilities. This means that you have the probability of x being equal to 1 plus the probability of x being equal to 2. Now, as you might recognize, the cumulative distribution function of a discrete random variable can be generated from the sum of the probability mass functions, right? So the sum of the corresponding probabilities functions at the point of the realizations. Okay, so I'm going to define this a little bit more, or basically illustrate that a little bit more accurately. But you can see this quite here. So this is basically going to be constructed from the sum. The probability that x is equal to 1 is going to be, or is 0.5 in this case, and the probability that x is equal to 2 is 0.3. So that's going to be 0.8, of course, but that's just, you know, a side note here. You understand this? So this is how you can address basically specific values of a cumulative distribution function. In general, of course, if you put in k, that you're going to get back the probability that the random variable is not greater than that. So I will use that basically for the definition of a cumulative distribution function. Let's say at point k of a random variable capital X, so you always have a random variable basically attached to it, is going to be the probability that the random variable is not greater than k. That's what it's going to be. All right? Is this understandable? And this exists for both for discrete as well as continuous random variables. For discrete random variables, as you saw from the previous example, this is going to be at point k the sum of the corresponding, basically, of the corresponding probability mass functions, right? So at point x, with respect to x, so you keep in mind, guys, fx is the probability mass function of the random variable capital X, and at point small x, basically, you need to sum up these points, but only for those. So again, keep in mind, guys, x is a summation index, and this is basically, you know, taking discrete values. So you take them all, basically, but only one condition: it must be less than or equal to k. So whatever you basically use k, this is the way to do it. You understand this? So this is kind of weird, because you might ask yourself, okay, what's the summation index? And let me tell you this: summation index is going to be x. Okay, we take that. Okay, it simply is. All right, for those for which basically that is not greater than k. All right, so that's that. Without loss of generality, of course. So summation index cannot be basically, they must be integers, technically speaking. So 0, 1, 2, 3, 4, this and that. But if it's different, you can also use that one as well. Okay, so this is not an issue. Do you understand this, guys? So this is basically what was from the previous example. I will come back to another one. Okay, so don't feel confused. Now, what about basically the issue if x is not discrete but continuous? Now, if x is continuous, then most of the time it will have a so-called probability density function. Everybody should know, or at least you supposed to heard of, you know what a probability density function is. Not every basically random variable that is not discrete will have a density function, but most of them do. So most of the time, this is how it's going to be. And then this corresponds, so this is the continuous analog, let's say. Okay, so keep in mind, guys, I change it. So I'm not going to distinguish, as far as this notation is concerned, between density functions and probability mass functions of random variables. So you need to figure out which is basically what from the context, guys. You understand what I'm saying? So if the random variable is continuous, then fx is going to be a density function most of the time. And if the random variable is discrete, then fx is going to be a probability mass function of the time. All right? So most of the time. Again, if I change it, then I'll basically let you know. You understand this, guys? So you need to figure out which is basically from a given context. But again, most of the time, the random variable is either discrete or continuous. There is also a third case where you have neither, but in practice, that's not, you know, something which is going to be important for you. So again, most of the time, you have either discrete distributions or continuous distributions. And I don't consider the cases neither. Now, the sum is going to be replaced by an integral. The integral starts, let's say, at point minus infinity. That's not a point, but you can simply just assign that. And then it will stop at point k, because k is the argument that you put into the CDF. All right, so you take basically just the integral. That's going to be an area, because the probability density function is a non-negative function, of course. So if you take the integral of that, this is going to generate an area from minus infinity to k, and that's something that you should basically have seen before. Is that the case, guys? So let me ask you this. Show hands who has seen this before in terms of, you know, a continuous distribution. Let's say the normal distribution. All right, okay, I'm fine. Thank God you have seen this before. Okay, so then if you haven't seen this before, then I would recommend you watch other videos, maybe about maybe the normal distribution. Anyway, note this, guys, and this is going to, sometimes I'm going to use that one in terms of differentials. So this is a differential, of course. You can simply say that the density, if you want to connect the two, that the density function okay, attached to the differential x. X is the integrated, guys, so x is an integrator, all right, is going to be the basically the differential of the CDF, of course. So if you basically you're kind of confused, the derivative, right? So that's basically the issue what you have here. The derivative of the cumulative distribution function is going to be the density function, provided that the cumulative distribution function is or can be differentiated. All right, so this is the general context that I'm going to look at. So and this equation basically is equivalent to that one. This is a differential notation. So in terms of differentials, right, maybe you have seen differentials equations, maybe, so you could basically that. And then this is in terms of derivatives, all right, but that both are equivalent. All right, guys, keep in mind this is not a multiplication, okay, so that is abuse of notation, of course. That is a differential, okay, so there is no multiplication there. If I see you doing that, ooh, okay, I'm not going to basically penalize you for that, but you're not supposed to. You're not studying mathematics, of course. But again, anyway, you should basically distinguish between that. That's abuse of notation, but it kind of behaves that way. You can also call this the increments of the cumulative distribution function. So you can use the term delta in that case if you look at the discrete version of it, okay, of the jumps of the cumulative distribution function in the discrete case. But anyway, that's it. So yeah, this is what it would look like. Now I'm going to also consider another one, let's say a discrete random variable. So just regarding the definition, so how I'm going to apply this. So let's say I want to calculate the distribution function at point 2.5, not at point 2, 2.5. And keep in mind, guys, 2.5 is not a realization of the random variable because the realizations are 1, 2, and 4. Okay, so that's these are the only realizations that the random variable would have, but there is no other. Unfortunately, yeah, but it doesn't matter. So this is what it's going to be. Now, check this out. Okay, that's the formula. So I need to sum up basically every single probability mass function at a certain point where the point is not greater than 2.5. Okay, and these are going to be just two, namely that basically at point 1 and at point 2, and there is no other because point 4 is greater, 4 is greater than 2.5, and you're not supposed to. You understand how this notation works? Okay, so if you do, then you understand that as well. So again, I just want to basically show you that formula, how it works, and then you would have the same thing that I showed before. It's not a big issue. All right, so that's 80%. That's not going to happen still. Although keep in mind, again, so 2.5 is not a realization of the random variable, but that doesn't matter. Okay, so the cumulative distribution function is defined basically for every single point there is, even if the point is not part of the set of realizations of the random variable, which is generally the case in the case of discrete random variables as you might see it. All right, you need to take those realizations that are not greater than 2.5, and you need to take the cumulative distribution, you need to take the probability mass functions of those, and then you cumulate them. This is how you basically, you do it. Is this understandable? All right, so that's what you have, or you're supposed to do. Now you're supposed to also know how this works for continuous ones. The normal distribution is basically denoted by two parameters, namely by the mean and the variance. Okay, you've seen this before. If basically a random variable follows a normal distribution with mean 0 and variance 1. So again, keep in mind, this is the mean. Okay, I will talk about that later. And this is the variance. Okay, I will also address that one, right? So then the random variable is going to be standard normal. You know that, right? And the standard normal distribution has a density function, which is going to look like this. I call this phi. So if I say phi, I usually mean the density of the standard normal distribution. You can call this also f. It doesn't matter, but I call it phi in general because that's a very common density. Let's say it's going to be, of course, 1 by the square root of 2 times pi times e to the power of negative 1/2 times x squared, guys. Okay, of course you don't need to know where pi or the all this number would come from. This is not going to be an issue. trust me on this, guys, you don't need the density function of the normal distribution to pass this course, okay? So you don't need to take integrals of that, okay? It's not going to happen because there is no way to do that, but that's something that you have seen this before, right? And you also know how this would look like, so I assume you have seen that. Now, of course, for the cumulative distribution function, again, for the standard normal distribution, I use capital Phi. So anytime you see capital Phi, that's going to be, in most of the cases, this is going to be the cumulative distribution function of the standard normal distribution. Now, you cannot write that down explicitly. You can only write it down implicitly. That's going to be, according to this formula, this is going to be the integral at point 1.96, for example. This is going to be the integral from minus infinity to 1.96 of the density function of the standard normal distribution. Now, again, so there is no way for you to address it other than numerical one, or you can look into the tables. You have seen the distribution tables, right? So it's going to be about that. So I will show you how this works. I mean, there is a table you can of course, yeah, I mean, you can see in the book. So in the book that I have uploaded, guys, so I need to charge it, sorry. There is a distribution table for the cumulative distribution function of the standard normal distribution function. Everybody should know how this works, all right? So you've seen this before in statistics, right? This is how it would look like. So you can see there I was cutting off here in the middle because it would be too big on the slide. So you go to line 1.9 and you go to the column 0.06 where you find this in the title. Why? Because 1.9 plus 0.06 is 1.96, of course, and there you find a probability which is 0.975. So 0.95 is basically the value that comes out if you put in 1.96 into the cumulative distribution function of the standard normal distribution. Now let me ask you this, guys. Everybody has seen this, right? Okay, all right, for real? Okay, okay, good. If you haven't, then watch the videos, okay, related to that, because again, everybody should know how the standard normal distribution works, okay, at least basically on this part, okay, so you don't need to waste some time, calculate integrals numerically, but that's what you're actually doing, okay, in this case. You look at basically the integral from minus infinity to 1.96, or actually the area of the density from minus infinity to 1.96, because, again, the density function, just as every other density function, is a non-negative function. So if you integrate a non-negative function, you're going to get back the area with the x-axis of that function. All right, is it clear? All right, so that's something that you've seen before, I assume, and I hope that you did. And yeah, so again, graphically, since it's the area, the density function of the standard normal distribution looks like this. I think everybody has seen this before, right? It's, I mean, what major issue is, it is symmetric with respect to the y-axis, so everybody should know that. If you take basically the area from minus infinity to 1.96, which you actually do when you put 1.96 into the cumulative distribution function, you're going to get 0.9675 back. So this purple area is approximately, right? It's not exactly, but approximately 0.9675. Is it clear, guys? Okay. Now, if this is 0.9675, now let me ask you this. This is not on the slide, but this is not just, you know, my actual question here. The tiny red area, how large is the tiny red area if the purple area is 0.9675? Huh? That's right. So you have 2.5% basically on its right. So if the area, the purple area is 97.5% of the total area is equal to 1, of course, right? Then the tiny red area to its right, 1.96, is going to be 0.025. Is this understandable? Because the total area of any density function is equal to 1. That's something that you should need to. So there are two major characteristics of the density function. Number one, it's not negative, and number two, the total area of it is going to be equal to 1. Is this understandable? All right? Yeah. Okay, that's fine. Now, if basically you have the area coming out, which is 0.9675, at point 1.96 of the cumulative distribution function. On the other hand, you can say that 1.96 is the 97.5% quantile of the standard normal distribution. SND denotes the standard normal distribution. I was too lazy to write it down. All right, but that's not official abbreviation, but I use it quite a lot of times. Is this understandable? So if you put in 1.96 into the cumulative distribution function of the standard normal distribution, getting 0.9675 approximately, then you can say that the 97.5% quantile of the standard normal distribution is equal to 1.96, because 97.5% of the distribution is not greater than that. Greater than what? Greater than 1.96. You understand what I'm saying? So basically 97.5% basically are to its right. Is it clear, guys? Okay, so they don't pass basically the distribution. All right, I'm glad that you've seen this before. Now let me just do expectations and let me just recall what these are. Now of course this is not an exact definition, this is an implication. Okay, so it's not a definition, but again, due to the scope of this course, I will consider it to be the definition. I will only distinguish between these two cases, whether x is discrete or continuous. If it's neither, then we just simply pass it, okay, because that is not going to be an issue in practice. If x is discrete, then the expectation, this is how I denote it, of the random variable is going to be the weighted sum of its realizations. So you need to basically take the realizations of the random variable, you need to know what they are, and you need to multiply them by the corresponding probabilities, getting the weighted sum of the realizations weighted by the probabilities of the realizations. Okay, so this is what you're going to see. So x is a realization of the random variable, and if you basically multiply the realization by the probability density function at the same point, you're going to get the weighted, and then you sum it up with respect to the realizations, then you're going to get the weighted sum of those realizations, and that's going to be the expectation of the random variable. Okay, I think you've seen this before. I'm going to do an example to this. Keep in mind fx is the probability mass function this time, and if the random variable is continuous, then of course I would need to express this in terms of its density. So you take the integral from minus infinity to plus infinity, which is the total integral in the total range. Most of the time, for example, the normal distribution has a support of minus infinity to plus infinity. So you take x times the density, and then you integrate this with respect to x, and that's going to be the expectation according to this. But keep in mind, fx is the density function this time. This is basically how you calculate the expectation of the continuous random variable. Those are basically, this is basically its continuous analog. So all you would need to do is replace the sum by an integral, and you replace basically the probability mass function by the density, and that's it. And then you integrate it with respect to the realizations from minus infinity to plus infinity, yielding the expectation of a continuous random variable. Guys, you were supposed to have seen this before. I'm going to do this basically for example. Now, the variance is the expectation of the squared deviation of a random variable from the mean. So what you're doing is this: you take the squared difference between the random variable and its expectation, and you take the expectation of this. I'm going to give you an approach how to do that basically. Okay, so how would you basically adjust this? But you can also bypass that part by simply taking the expectation of the squares minus the square of the expectations. Let me repeat, the variance of a random variable, and I'm going to use this formula more often. Sometimes I use the former, but most of the time I'm going to use the latter. This can be shown, by the way, so you don't not need to, is the expectation of the square minus the square of the expectation. Okay, and depending on whether x is continuous or discrete, you would calculate basically the variance accordingly. I'm going to show you how. Okay, but you're supposed to see in this formula also. So again, what you would have is the mean. Check it out. So if you look above, this is just an interpretation. So this is the mean. If I say expectation, you can also say the mean. The mean of the squared differences between the realizations of the random variable and its expectation. This is what the variance is. All right, so you can say the centralized second moment, of course, whatever. All right, so yeah, and this is what it's going to be. And then, of course, you can also calculate the standard deviation from it by simply just taking the square root of the variance. Is this understandable, guys? Now, you're supposed to have seen this before. I'm going to show you this one, okay, for the discrete and as well as the continuous example. The variance, as you see, again, so if the variable is discrete, the variance is going to be just The mean of the squares minus the square of the mean. This is a theoretical variance, so I'm going to distinguish between the theoretical variance and empirical variance. The theoretical variance is, again, based on expectations. So you'll have basically, if you take the expectation of the square, this is going to be the weighted sum of the squares. Okay, so you take every realization there is, you take its square, and you weight it by its probability mass function at that point. Okay, so at the point of the realization. This is the mean of the squares, right? And then after that, when you're done, you subtract the square of the mean, and then you get back basically the variance of the random variable. This is the way to do it. You can also use the former expression, but I'm basically use that one. This is a more common one. Again, mean of the squares minus the square of the mean, or the expectation of the square minus the square of the expectation. This is how it's going to be. And if the random variable is continuous, then its variance, again, is simply also mean of the squares minus the square of the mean, or mean expectation of the square minus the square of the expectation, but you replace the sum by the integral, and of course from minus infinity to plus infinity, because you need to calculate the total integral, okay? And then you take x squared times the density, so that's what it's going to be, and you calculate the integral with respect to x of that. This, okay, so this expression is the expectation of the squares, and then you take minus the square of the expectations, or the square of the basically of the expectation, right? And that's going to be the variance if you have a continuous random variable. Is this understandable, guys? Okay, so again, I will complete this one at least, so you'll see the moments, and then I'm going to put the linear transformations as well as the transformation theorem for tomorrow. So you're going to see that one tomorrow. I will re-edit the slides, so you're going to see that one as well. All right, now let's see. Okay, so this was the probability mass function of the discrete random variable. The expectation is going to be, and this is what you see, the weighted sum of its realizations weighted by the probability mass function. So you take 1 times the probability of 1 plus 2 times the probability of 2 plus 4 times the probability of 4. This is what it is. Now, if I'm not mistaken, guys, I got 1.9, so for the expectation of this random variable, and the variance is going to be used accordingly. This is going to be the expectation of the squares minus the square of the expectations. So you'll have basically the realization to the second. 1 squared times the probability of 1 plus 2 squared times the probability of 2 plus 4 squared times the probability of 4. This is the expectation of the square of the random variable. You see that, guys? And then minus the square of the expectation, which is minus 1.9 squared, if I'm not mistaken, guys. And if I did it correctly, the variance is going to be 1.29. You've seen this before? Again, so I wanted to basically recall that. Then, of course, the expectation of a continuous random variable, for example, for the normal distribution, is also calculated from the density of the variable. So you have basically the total integral of basically of x times the density function with respect to x. Now, you can use integration by parts, partielle Integration, if you know the German term, right? So it's relatively easy to show, but I skipped that one. So I don't want to basically waste some time on that, because this is not the main focus on this course. So your major is not going to be about integral calculus, okay? It's going to be about time series, right? So, but I need to drop integrals here and there. And if you do integration by parts, so let's say this is one function, this is the other, and then you can split it, right? So let's say this is u, this is v prime, and then you could basically address those, right? Or the other way around, it's depending on the consideration. But it's not about that, so you can also calculate the substitution by using, even better, substitution would be even better than that. If you basically do that one, you get 0 as a result. All right, so trust me on this, but that's not going to be an issue for you, okay? Either integration by parts or basically substitution. Maybe substitution would be better. Now the variance, again, so if you do that, this can be shown, by the way, the variance of a standard normal random variable, again, just like every other continuous variable, is going to be calculated by x squared times the density of the total integral of that, basically, and this is what it is, with respect to x, of course. So then you have the expectation of the square minus the square of the expectation. Now, of course, the expectation was 0, so each square is going to be also 0. And if you finish that, again, so this is either, I mean, that's also not difficult to do. It's quite long, but it's not difficult. So then it's going to be equal to 1. So that's something that you can show, by the way. All right, guys. So this is as far as continuous random variables are concerned. You can do with the other distributions as well, but that's what it is. I skipped that one. I don't want to do it because, again, your major is not going to be about integral calculus. We're going to do time series, but sometimes here and there, I would need to drop some integrals as well. Yeah. You got questions related to this? No questions at all? Okay, so again, I'm going to do the rest tomorrow. I hope to see you tomorrow, 8:30, same time. Yeah, we're going to use the same room. So, yeah, I hope you'll be there, guys. Yeah, all right, that was it. Thanks. Okay.